will start the recording, and we will begin. Okay. Uh, my talk is about Kepler and Galileo, and their relationship to each other, and their relationship to the scientific revolution. The talk will be in three parts. The first part will be about the life and work of Kepler. His work is certainly his life is a little bit less well known than Galileo. Second part will be on the life and work of Galileo. Obviously, we can just touch upon the highest points, especially a life like Galileo's. And then the third part will be wrapping up, talking about the relationship between these men and their relationship to the scientific revolution. So, Kepler, the founder of modern celestial mechanics and geometric optics. He was born to a innkeeper family, rather poor, but he was lucky enough to show mathematical abilities early enough that he won a scholarship to the local university. And in particular, he was given really a very fine education compared to, the resources, the financial resources that he had. We'll see as we go through this, and I read some of some of his works. You'll see what I mean by him having a mystic temperament, developing a deep Pythagorean faith in the mathematical construction of the universe. This really will drive his life and his work. For example, he asked very interesting questions that were not asked before, like why are there 6 planets? Well, what do you mean, why are there 6 planets? There are 6 planets, or if going back to the Greek days and the medieval days, there were actually 5 planets or 7 planets if you wanted to count the sun and the moon. But question wasn't why, it's just what we saw in the sky. What determines their relative sizes and the periods of their orbits? Again, this was not a question. It was something of studying the sky and building models upon what we saw. Ptolemy has a model, Copernicus has a model. It wasn't a question of why, what determines these sizes and periods. It just is what we find when we study this, and we're able to build a model to accommodate that. The third question is, in fact, an interesting question, which was a real question. Why do they move the way they do? Well, that question was answered. That was answered by the ancient Greeks, was answered with the same answer right up through the Middle Ages and the Renaissance, right through Copernicus. Copernicus never asked this question. The answer was that in the perfect ether that the celestial world was made from, their natural motion was in circular motion, uniform circular motion. That was their natural motion, and that's what we see in the heavens, and that was the end of it. There was no more. It was no more investigation than that in terms of that why question. We'll see that Kepler introduces a very, very radical question to that. He has no interest in such answers about just natural motion. That's the way we find it. He wants to actually find the forces involved in making the planets move the way they do. Doesn't sound radical to us because he's the first one to ask that so long ago. To give you an insight into Kepler, I'd like to tell you a story about his early teaching. He actually like I say, he had a fine university education taught by one of the most prominent astronomer mathematicians of the day at the university that he was at in Germany, a man by the name of Maslin. So he got a very professional education as a mathematician and an astronomer. Remember, in those days, astronomy was a part of mathematics. And Maslin suggested that he take a job towards the end of his studies to maybe make some money, and he actually took a job as a high school math teacher. And the story goes that he's teaching one day about the conjunctions of Saturn and Jupiter. They happen very regularly, about every 18 or 19 years. And he's at the blackboard, as the story goes, and he has the zodiac as a circle of 1. And for example, here we would have the first conjunction here at this place on the zodiac, and then there would be a second place 18 years later. Here the conjunction would be here, and then the third conjunction would be here, and then the fourth conjunction would be here, and the fifth conjunction here, and so on. And as he's drawing this, he's seeing what mathematicians would call an envelope, right, to a circle, a tangent envelope to a circle. And he takes a quick calculation of just how big that inner circle would be compared to the large circle, if you call that 1. He finds that circle, given these conjunctions, to be 0.53 of the bigger circle. Well, he's astounded by that because that's exactly the ratio, according to Copernicus, of the ratio of the orbit of Saturn compared to the orbit of Jupiter. He gets very excited, and sorry, as he dismisses the class and starts working on a scheme like this. He takes the orbit of Saturn and the orbit of Jupiter and puts a beautiful equilateral triangle inscribed in that. And once he has the equilateral triangle, he can inscribe the orbit of Jupiter. And once he has that circle, he can, since he starts with an equilateral triangle, he can then go to a perfect square. Once he has that square, he can inscribe a circle in that, and that should give him the orbit of Mars. And then he's got a triangle, a square. He'll go to a pentagon and go ahead and inscribe that, then inscribe a circle in that, and that should be the orbit of the Earth. He's very disappointed that this didn't work. This scheme did not work. This was not God's plan. So he says, not giving up, he goes to 3 dimensions. He says, after all, these are 3-dimensional orbs in the sky. And as a well-trained mathematician, he knows that the last theorem in the last book of Euclid proves that there are only 5 regular solids, right? Solids are all made from equilateral surfaces. There would be 3 made out of the equilateral triangle, the tetrahedron, the octahedron, and the icosahedron. 1 out of a square, the easiest one to think about, the cube, and finally 1 out of the pentagon, which would be a duodecahedron. Now, this is an inherent property of space, proven by Euclid. And then, of course, it occurs to him, I've got 6 planets and I've got 5 perfect solids. Why don't I again start with the orb of Jupiter? Start with the orb of Saturn, and begin to see how I can inscribe these perfect solids, which will then give me a platform to inscribe another orb in that. And I can pick then another solid, which will give me the opportunity to inscribe another perfect sphere in that. And by playing around, he devises a model which to him is close enough satisfactorily to this is the plan of God. And this stays with him his whole life. It's not perfect. He knows it's not perfect. Some of the ratios work out better than others, but this idea that he is looking for the mathematical plan that God has used to create the universe. And it is his destiny, his mission to find this. This, by the way, gives us the first opportunity to talk about the first contact between Galileo and Kepler. Kepler writes the book Mysterious Cosmos, in which he has this model in it and much else, a lot of mathematical speculation, a lot of calculating of orbits. And he's very proud of this book, and he wants to send it around. He's just a young 25-year-old high school teacher. And the story goes that the ambassador to Italy is heading out just around this time, and he gives a couple of copies of the book to the ambassador and says, find someone in Italy who would be interested in my book. Ask around. And it turns out that he gives the book to Galileo, a professor at Padua. Certainly not a nobody. He holds the chair of mathematics at Padua. Galileo writes a very, very nice letter back, very polite letter back, supporting the young man. And I would like to read to you a piece of the letter, because it'll give you some of the spirit of Galileo. Let me switch glasses if I can to a stronger pair. It is not days, but only a few hours that I have received your book, which was brought to me by Paul Emerson. And Paul mentioned that he was returning to Germany. So I thought it would really be taken as an ingratitude if I did not, by this letter, express my thanks for your gift. So please accept my thanks, and moreover my gratitude for you having by this means graciously invited me to become your friend. So far, I've only read the preface to your book, from which, however, I got a little insight in what you intend by it. Really, I congratulate myself with all my heart to have such an ally in searching for the truth, such a friend too of this same truth. I should rather congratulate you for all the beautiful things that you present in support of the truth. I shall only add this and promise that I shall study your book patiently, being certain that I will find in it marvelous things. This I will do more joyfully, and that I have for many years past subscribed to the teachings of Copernicus, and from it I have been able to demonstrate causes of many phenomena, which without doubt cannot be explained by the traditional hypothesis. I have worked out proofs, as well as computations of contrary arguments, which, however, I thus far dare not share publicly, for being frightened by the fate of our own master Copernicus, who thought, having gained immortal fame in the eyes of a few, had been ridiculed and exploded by innumerable others. For so great is the number of fools. I should indeed venture to disclose my opinion if there were more men like you, but since there are none, I shall desist from such a task. Now, does that sound like a man who will not write to that young astronomer again for 12 years? But that is the case. This is the first letter of Galileo to Kepler, such an enthusiastic support of this young scholar, clearly thanking him for his friendship, but yet he will not write again for 12 years. Kepler does write back, of course, back to the chair of mathematics at Padua, and says, "Please join us. Don't be timid. With your arguments, you would be at the same time help your comrades who endure so many unjust judgments, for they would obtain either comfort from your agreement or protection from your influential position. It is not only you Italians who cannot believe that they move if they do not feel it, but we in Germany also do not by any means endear ourselves to this idea." And he goes on, again, trying to set up some kind of a regular relationship with Galileo, but to no avail. Galileo does not respond. He does end that letter by saying, "Farewell, and answer me with a very long letter." But it does not happen. Kepler also sends the mysterious cosmos to Tycho. Tycho Brahe, the most famous astronomer in Europe. Everybody wants to work for Tycho. He has this incredible observatory on the island of Ven. It's a dream of any young astronomer to go work for him. He sends a copy of the book to Tycho, basically as a job application, and Tycho was impressed. He's not impressed with all the mathematical mysticism or why there are 6 planets and things like that, but he is impressed with this young man who can compute orbits. And he doesn't have someone with that kind of mathematical strength on his staff. So he actually invites Kepler to come in to visit him, which Kepler says he cannot do right now. Denmark is much too far away. He can't afford it, but he approves. He thanks Tycho very politely for the invitation. However, he does finally reach Tycho. I'm sorry. I think did I go past? Yeah. Sorry. I didn't finish this slide. Tycho finally is basically booted out of Denmark by the succeeding king, who didn't fancy supporting Tycho in this tremendous lavish style that he had become accustomed. So in searching around for another patron, he does find the Holy Roman Emperor, Rudolf II, in Prague, someone who will be very, very happy to have the most famous astronomer in Europe come and grace his court. So in 1600, Tycho does come to Prague and again invites Kepler to visit him. And now, Prague being much, much closer, he does in fact come and joins Tycho's staff. They don't get along very well. One is the pure mathematician disguised as an astronomer. The other, Tycho, being the greatest naked eye observational astronomer in history. They have completely different agendas. But as history would have it, Tycho does assign Kepler the orbit of Mars, which is the most difficult orbit to fit into his system. Remember, Tycho's system is one in which all the planets go around the sun, but yet the sun continues to go around the Earth. this keeps the Earth stationary. Mars was the most difficult planet to fit into his model. It was the most difficult planet to fit into Copernicus's model and in Ptolemy's model. Of course, we know now why, because of all the data that we have. Mercury, there was very little data about Mercury in any of these times, being almost always lost in the glare of the sun. There was great data on Mars, particularly from Tycho, and it is the most elliptical of all of the planets. So if you're trying to fit this into the beautiful circles and combinations of circles dictated by Aristotle's cosmology, you are going to have a hard time with Mars. Tycho dies just about 18 months later after Kepler joins him, and by some miracle, the emperor does anoint or appoint Kepler as his successor. You can imagine that was not easy. Tycho had a whole staff, many people with him much longer than Kepler. Kepler had a fight with Tycho's family to get a hold of the data, which they saw could be very, very valuable. They could try to sell it or whatever. But it seems that from the intervention of Rudolf II, he was in fact appointed to the imperial mathematician, to the court of Rudolf II, by the way, with 1/4 of Tycho's salary, and did have access to all of Tycho's data. He then works on the orbit of Mars. And it's a long, long story, which we have no time to go into. But finally, in 1609, he publishes one of the most important works in the history of astronomy, Astronomia Nova, the New Astronomy. And his full title is very interesting. It's the New Astronomy based upon the causes of celestial physics, treated by means of commentaries on the motion of the star Mars from the observations of Tycho Brahe. The phrase celestial physics had never been used before. There is no such thing up until the mind of Kepler that there was a celestial physics. There was, according to Aristotle and according to the cosmology taken over into the Middle Ages and later, there was terrestrial physics, the world of earth, air, fire, and water, and how those bodies and combinations of those bodies would behave according to forces in motion. And then there was the celestial world, which was made of pure ether, that there was no physics involved at all. It was all perfectly natural, circular motion, uniform circular motion, and combinations thereof. There was no physics involved. And the two studies, the study of the physics of the terrestrial world and the celestial world, were two completely different subjects. Actually, the word physics was coined by Aristotle, and physics was in the world of natural philosophy, studied by philosophers. And as I mentioned before, astronomy was in the one of the branches of mathematics. It was a branch of pure mathematics. And so these two worlds did not touch until we find Kepler wanting to talk about the celestial physics of the planets. So in this great work, just the bullets that are so important among the many, many things going on in here, is that he completely abandons the idea of celestial uniform circular motion. Not for lack of trying, he tried for years. There's the famous story of the 8 minutes of arc, that once he did finally have a circular model for Mars and computed various positions, he found that one place in the orbit, his calculations were off by Tycho's measurements by 8 minutes of arc, which would have been just fine for Copernicus, just fine for Ptolemy. But he writes, no, since God has given us the gift of Tycho, we have to say, no, this model can't be right. Tycho would not be off by 8 minutes of arc. We need to start again. So he shows that, in fact, the orbit of Mars actually contains the plane of the sun, as certainly the Earth does. He comes to the realization that it is the sun that is, in fact, the seat of all the motion of the planets. He concludes that, in fact, it's a magnetic force, kind of the unknown force of the day, and that somehow or other there's a magnetic force in the sun, that maybe there's a magnetic force here in the planets in which the revolving sun, he posits that the sun is revolving on its axis. The revolving sun is sweeping the planets around by this magnetic force. So this is the new astronomy of 1609. A very important year in the history of astronomy because it was also, oh, okay, I'm ahead of myself. Let's just mention the two laws that are in that work. There's the first law that the planets in fact move in ellipses, that they do not move at constant speeds, and that the sun is at the center, is at the focus of one of the foci of the ellipse. And the second law being the great area law, in which if you have a radius line from the sun to any planet, it will sweep out equal areas in equal times. And this brings us to the second contact that Kepler and Galileo have. They never met. They've only exchanged letters. And here is the occasion where we have the second set of letters between them. Because at the same time, 1609, that Kepler publishes his new astronomy is exactly when Galileo points the telescope to the stars, to the moon, and produces the Starry messenger, which is a revolution in our understanding of the universe. Galileo becomes the most famous scientist overnight in Europe with the Starry messenger. It sells, the first edition sells out immediately, and it is the buzz all over Europe of the incredible discoveries that Galileo first makes with the telescope. And you know, the discoveries are, first of all, about the stars. He looks through the telescope, he sees more stars than you see with the naked eye. He sees that the Milky Way is, in fact, not some kind of a cloud, not some kind of atmospheric phenomenon. It is, in fact, a myriad of stars so close together that it looks like the Milky Way. He looks at the moon, and to everyone's aghast, the moon looks more like the Earth than like the perfect ether that it was supposed to be. It has mountains and valleys. It has seas, these dark areas that he calls Mara, like the Sea of Tranquility, where we had the first moon landing. And he saves the best for last, which is the four moons of Jupiter. So we'll talk a bit more about that a little later. But I would like to read his letter to Kepler, because Kepler is the first one to actually support him with these astounding discoveries. There aren't very many telescopes around right now. People don't know what to make of turning the celestial world upside down like this. And so he writes to Kepler. He says, "You are the first and almost the only person who, even after but a cursory investigation, has, such as your openness of mind and lofty genius, given entire credit to my statements. We will not trouble ourselves about the abuse of the multitude, for against Jupiter, even giants, to say nothing of pygmies, fight in vain. I think, my dear Kepler, we will laugh at the extraordinary stupidity of the multitude. What do you say to the leading astronomer of the faculty here, to whom I have offered thousands of times of my own accord to show my studies, but with the laziness, the obstinate laziness of a serpent who has eaten his fill, they have never consented to look at the planets, nor the moon, nor the telescope. These are great matters that they do not have occasion to surprise. People of this sort think that philosophy is a kind of a book, like the Aeneid or the Odyssey, and that the truth is not sought, not in the universe, not in nature, but by comparing texts. Oh, my dear Kepler, how I wish that we could have one hearty laugh together. Here at Padua is the principal professor of philosophy, whom I have repeatedly and urgently requested to look at the moon and the planets through my glass, which he has perniciously refused to do. Why are you not here? What shouts of laughter we should have at this glorious folly. And to hear the professor of the philosophy at Pisa laboring before the Grand Duke with logical arguments, as if with magical incantations he could charm the new planets out of the sky." Again, it's a beautiful letter. It's a, thanking Kepler. Notice the shoe is now on the other foot. Now all of a sudden Galileo is looking for support, and Kepler comes through as the imperial astronomer of the court of Rudolf. It's a very, very important support that he gets at this time. As he says, you're one of the only people who actually support me. But again, I've read large excerpts of the letter because I want to ask you, does that sound like the kind of letter that you write to a colleague? And clearly, that is a very collegial letter talking to an equal. Does that sound like the last letter he would ever write to that colleague? But yet it is. We only have 2 letters that Galileo wrote to Kepler. So we'll look more at the starry messenger discoveries when we get to the life of Kepler. I like to move on. One of the things, Kepler finally gets his hands on a telescope, one of the Galilean telescopes, and he makes a study of it. He had already written a book on optics, studying lenses, and he goes ahead and does a theoretical analysis of this, tries different kinds of lenses, and comes up with a new design for the lens, where we're using 2 convex lenses as opposed to Galileo using a convex and a concave. It would seem historians of science seem to agree that Galileo just kind of put this telescope together by trial and error. His telescope, the Galilean telescope, he was very, very good with his hands, very talented with his hands, and not surprising, he taught himself how to grind lenses and all the rest. But Kepler, whose actually eyesight was very poor, went ahead and when he got his hands on the telescope, he actually asks Galileo for a telescope during this exchange about the starry messenger. And Galileo says, "Yeah, I'm sorry, Kepler, I can't afford to give you one. I've given them all away to my patrons. I'm sorry, I don't have one to spare." This is the imperial mathematician of the Holy Roman Empire. This is, supposed to be his friend, his colleague. He doesn't have one to spare. He's too busy, giving them away as gifts, trying to improve himself. But anyway, Kepler does make this theoretical analysis publishes it called a dioptrics, very much an Euclidean kind of treatment, very standard, kind of theorems and definitions and proofs, and very dry, very different from the kind of stuff that you should expect from Kepler. And he comes up with the design that we now basically call the refracting telescope. Obviously, there have been many, many improvements since, but that fundamental design is what we have from Kepler. Here in 1611 is when Kepler's life takes a very dark turn, and I'll just mention some of these things briefly. In 1611, his wife dies, some of his children die from the plague. The Emperor Rudolph has to step down. He abdicates, and his brother takes over. His brother is no fan of Kepler. Wants to keep him on to do horoscopes when it's at his convenience, but the staff is all gone, and the observatory is all gone, and basically, makes it very uncomfortable for Kepler to stay in Prague. And he moves out to a small provincial town, to Linz, and again winds up starting to teach high school again. He's back to where he started from. He still nominally has this title, and he still can make some money by casting horoscopes to the nobility and whenever the emperor wants a horoscope. And he's supposed to be on the emperor's payroll, but that doesn't work out very regularly. And so Kepler really falls on very hard times and falls mostly into poverty. He does remarry, has more children, continues to produce the incredible works that we'll see in a moment that he produces, but in terms of his professional life, his professional environment, it's really quite incredible that he's able to do this. And so in 1619, again, out of nowhere, he continues his researches, he continues studying Tycho's data, and he finds yet another very important law. He finds actually lots of laws in this new work of 1619 called the Harmony of the World. He finds all kinds of series, geometric series, arithmetic series that connect the orbits of the planets with, with the periods of the planet, and looking at different kinds of progressions. He has all kinds of mathematical speculations that he tries, and buried in all that is what we now call his third law, that he called the Harmonic law. And that is that the period squared divided by the major axis of the ellipse, usually called A in mathematics, that distance from the center of the ellipse out to the perihelion, that cubed is the same number over and over again for each planet. And there's the modern data that we have for that. um, and this is really the first universal law that we have in history. Here is a law that is satisfied in all of its particulars by every single planet. It is the same number that comes up again and again. And this is a strange law. It looks more like numerology to the astronomers than anything else. But there it is. He has an interesting quote that I want to give you a little bit of the flavor, more flavor of Copernicus. I'm sorry, of Kepler. He says, geometry is co-eternal with the mind of God before the creation of things. It is God himself has supplied God with the models for the creating of the world and has been directly transferred to man with the image of God. Again, this is Kepler, is a very unique figure in the history of science, that he is so driven by trying to unearth the mathematical plan of God. To give you one more flavor of Kepler before we leave him, I wanted to quote another piece of his writings about when he found this third law. And again, if I can switch glasses so I can read it better. This is a paragraph from right before he introduces the third law. He says, now since the dawn 8 months ago, since the broad daylight 3 months ago, and since a few days ago, when the full sun eliminated my wonderful speculations, nothing holds me back. I yield freely to the sacred frenzy. I dare frankly to confess that I have stolen the golden vessel of the Egyptians to build a tabernacle for my God, far from the bounds of Egypt. If you pardon me, I shall rejoice. If you reproach me, I shall endure. The die is cast, and I have written the book. To be read either now or by posterity, it matters not. It can wait a century for a reader, as God himself has waited 6,000 years for a witness. No one writes. No one has ever written like Kepler in a scientific work, and I don't think anyone has ever written since. But besides the incredible mathematics, the very advanced mathematics that he uses, because he is totally university trained, and he is, in fact, a first-class mathematician. Besides this incredibly detailed mathematical work, you will find many paragraphs like this as he describes his work. What the model can show in calculating these orbits. Here is I think a very impressive comparison of the orbit sizes that he computes compared to the modern values, which I got off of a NASA website. I know these numbers bounce around a lot, the sizes of the planets, but taking the Earth as one, he is able to compute these relative sizes of the orbits of the planets. He also continues to publish. He publishes a multi-volume work called The Epitome of Copernican Astronomy. It's a 7-volume work, which basically is the new On the Revolutions of Heavenly Spheres. It's the new Almagest. It is the new Bible of how you want to learn contemporary astronomy. If you want to learn the new system and his laws and how to use them, this is the work that you would study. And finally, his last work, this is a debt that he owes to Tycho. On his deathbed, Tycho made him promise that he would publish his data, and finally he gets around. He calls it the Rudolphian tables in honor of his patron, Rudolph II, but it's basically all of Tycho's data, publishing with his new laws, publishing how to use this data to predict the position of the planets. And this is something which the astronomers can understand. They can understand, working from the tables of Ptolemy, working from the tables of Copernicus. The idea of having astronomical tables is a very long tradition in astronomy. There have been many. So when he finally comes out with these tables, and how to use them, the astronomers say, okay, let's take a look at this, because this is the kind of math that I understand. Because you have to realize that the astronomers really didn't know what to make of the three laws. Matter of fact, you'll see for the next 50 years, from when they were published up to the time of Newton, they weren't really mentioned very much. The ellipses, well, the astronomers, of course, learned about ellipses when they studied Apollonius in undergraduate school, but they weren't used for anything. There was no applications for them. There was kind of a school exercise. The area law is very difficult to use. It's not easy to use the area law to find actual positions of the planets in their orbits. And the third law is, I don't know what, people didn't know what the third law was. It was more numerology than anything. So the astronomers did not find a way to know what to do with these laws, but the tables were something that they understood and actually began to establish Kepler's system as something very, very meaningful, because of the accuracy of the kind of predictions that you could make were unprecedented compared to anything that came before. And the great example would be his prediction of the transits both of Mercury and Venus in 1631. This is a year after he dies. He makes this prediction in the tables in 1628, and it comes about just as he predicted, with an accuracy that is, I say, totally unprecedented. And he says in that last work, my aim is to show that the heavenly machine is not a kind of divine living being, but a kind of clockwork, right? Something we associate with Newton, insofar as nearly all the manifold motions are caused by at most a simple magnetic material force, just as all the motions of a clock are caused by a simple weight. And he also show how these physical causes are to be given a geometric expression, and indeed he does. So that is a brief review of the life and work of Kepler. We could stop, Eric, if there are any questions.
Well, there haven't been so far. If anybody does have a question, if you'd like to speak it through your microphone, please use the raise hand functionality when you click on participants. If you can't find that, just type something in chat saying you want to raise your hand and I will call on you, or you may type your question or comment in chat. And I'm not seeing anything so far.
Okay, well, why don't we go on?
Nope, we got one.
Nope, there is one? Okay.
All right, Rick, go for it.
I think you have to unmute yourself, Rick.
I did unmute him.
But he has to do it on his side as well.
Okay.
You mean this, Rick?
Yeah. Hi, Rick.
Rick
Hi.
Hunter.
I thoroughly enjoyed your presentation, but I don't have a question. I just must have flapped my arm at the wrong time.
Okay.
Oh, no, it's Rick Hunter who has his hand up.
Oh.
All right, Rick, if you can figure out how to unmute yourself or type the question in chat. In the meantime, Don asks, do you believe today Kepler is still underestimated in his contributions still today?
No, I don't think so. When you read the vast literature on the history of the scientific revolution, he definitely has his due. He may not be as well known, of course, as Galileo. After all, Galileo is probably one of the most famous scientists in all of history. Maybe the only people who can compare to him is a Newton, a Darwin, an Einstein. So in that sense, he's not in the popular culture. But in terms of the scientific community, yes, I think he very much, his stature is very much established.
And Howard typed Giordino Bruno, 1548 to 1600 with a question mark. I'm not sure what the question is, but that's what he wrote. Oh, okay. And then Rick Hunter asked, didn't we just have a transit of Mercury like yesterday?
I don't think yesterday, but I'm going to throw that to Claudio. Claudio, we just had a transit of Mercury.
Oh, and in the meantime, Howard, do you mind clarifying your question? I'm not sure what you're asking. Oh, well, I'll answer for Claudio. We did have a transit of Mercury a couple months ago, but at least in our neck of the woods, it was clouded out. So, It was November 11th, Margot says.
Yeah, if there was a transit of Mercury yesterday, I think I would have heard about it. Not only I, but I suspect many, if not all of you, would have heard about it. Something like that is not. It's not an esoteric astronomical event. It tends to be high profile, and in the vast realm of clickbait landscape, you can bet there would have been notification of it across the media world. So, yeah.
They did a live stream
In November. Yeah.
in November.
Okay. Last call for questions. Yep. Matori says, was Kepler the first ever to use mathematical formula to describe natural phenomena? Had anyone ever done this before him?
Yeah, mathematical formulas really did not come in until we began to use symbolic algebra, right? All the mathematics before that were always was completely geometric. Even if you look at the later beyond Euclid, Archimedes, the Islamic astronomers, they all had a geometric base to how they described mathematical relationships, and we really don't see the symbolic algebra coming in until the time of Kepler. So it is a good bet. I'm not completely sure, but it is a good bet that you wouldn't be seeing what we would recognize as formulas written in algebraic format until the time of Kepler.
Oh, and Howard clarified that he had thought Bruno was burned at the stake for heliocentrism.
No, that's a big myth. He was not burned at the stake for his beliefs about astronomy. He was burned at the stake because he denied the divinity of Christ. That you don't do in 1600. He had a lot of beliefs, a lot of far out beliefs, a lot of very visionary beliefs. He was not a scientist of any sort. He was just whatever he was a thinker, a speculator. But no, he was not finally burnt at the stake for his beliefs about astronomy. That's a myth.
Okay, and Marjorie, you shot to the top of my list with an unmuted mic, but I don't see a hand raised. Did you have a question?
No, thank you though.
Oh, no problem. I'm going to remute you then. All right, last call. Any record of astrologers in asterisks attempting to represent the orbits of planets mathematically? From Claudio.
Well, astrology and astronomy, of course, came up together from ancient times, from the ancient Egyptians and Babylonians. At some point, they begin to separate. Somewhere in the Middle Ages, they begin to separate. The Islamic astronomers also were great followers of astrology. But by the time you get to a Kepler and a Galileo, Galileo would not do horoscopes. Kepler did for money. He didn't believe it. Matter of fact, he even had a reputation for being a pretty good predictor from his horoscopes, but he did not believe it at all. And so you see the separation coming during the scientific revolution, where astrology falls behind, it stays in its own little world, and only astronomy really moves on. I'm not sure if that answers your question, Claudio.
Yes, it does. Peter, the broader question I was trying to type with my clumsy fingers here was if we have any examples of because astrologers go back to, I want to say Egyptian times, but certainly Greek, Roman. Astrologers would have had a mortal interest in getting things right, because many of them were beheaded if they didn't get it right.
For sure.
Or worse, if I may say. You would think that mathematics and observation and prediction of celestial motions would have been of great interest to those who would prefer not to die. So I'm curious if by accident, but by virtue of observation, prior astrologers because as they say, before 1600, if you didn't believe in astrology, there was something wrong with you. After 1600, if you did believe in astrology, there was something wrong with you, or variations on that quote. One would think that there would have been some accidental overlap of prior astrologers making observations.
No, Claudio, if I can interrupt you, now that you've clarified your question, and now I understand the question. No, absolutely, the astronomers used Ptolemy's model when Ptolemy's model was current. They even went to Copernicus's model. Their job, right, was to determine what would be in the sky at what time in the future and the past, for example, and that would then determine the horoscope of the noblemen, the kings that they were putting horoscopes to. So they very much had a vested interest in understanding these models, being able to read these tables, being able to make computations so they could make their predictions of what the sky looked like at different times.
Okay, thank you very much, Peter. Yes, that helps clarify that question. Thank you. Or that answer, I should say.
Okay, so I'll continue, Eric.
Oh, yep. No questions, it seems. Go for it.
Okay, thank you. I'm concerned about running over time and keeping people much later than is polite. Okay, let us try to quickly go through just the highlights. My goodness, of Galileo's life. Galileo had a much more eventful life, as we know, than almost anybody at this time of history. But he was his father, in fact, was a noted musical theorist. And again, music was also one of the branches of mathematics at that time. Galileo was born in Pisa, but at 10 years old, his father moved the family to Florence, the capital city of Tuscany, and he was always very proud of being a Florentine. At one point, even as a young teenager, he thought of studying for the priesthood and went away to study in the seminary, but he and his father decided at some point that was not for him, and his father then sent him back to his hometown to Pisa to study medicine at the university there at Pisa. He did not do well at Pisa. He did not do well as an undergraduate. He was not an easy person to get along with. He, kind of bucked authority and asked a lot of embarrassing questions, didn't accept things on faith, just kind of made a general nuisance of himself to the faculty, and also didn't do very well in school. He did not apply himself, and in fact, he left the university without earning a degree. But he was lucky enough to be introduced to the court mathematician at Florence, the court of the Medici, a man by the name of Ricci. He was the court mathematician for the Duke. And he's the one who introduced Galileo to mathematics, to geometry. Remember, at this time, going to University of Pisa to study medicine, you would only get the most rudimentary introduction to mathematics. You might get the first 10 theorems of Euclid, and that's about all. So he was actually introduced to Euclid and was given apparently quite a thorough study of all of that, and then was then introduced, followed up to his own study for Archimedes. And interestingly enough, this is pretty much the end of his formal education in mathematics. Now, he is a math professor for 21 years, but in fact, he was never trained as a university mathematician the way, for example, Kepler was. It's fair to say that Galileo was actually self-taught in his profession. Well, because he, in fact, had no degree in mathematics, it was very hard for him to get any kind of a job. He kind of knocked around for 5 years, doing some math tutoring here and there. And again, through Ricci's intervention, he was able to get him a very, very low-level lectureship job back at Pisa. Well, he didn't do any better as a faculty member than he had as a student. The faculty remembered him quite well. Not in a good way. He hadn't really changed his attitudes or his ways. For example, one of the stories that comes out that he refused to wear the academic gowns that all teachers had to wear. He thought that was nonsense, and it was just the kind of thing that Galileo would do, just to, I don't know, to pick a fight, just to be contrary. And but he does, get a 3-year appointment, very tentative kind of appointment. He's got to earn his way in, and in fact, after 3 years, he is not renewed with that appointment. I failed to say that while he was knocking around, getting odd jobs here and there, tutoring and whatnot, he actually was able to prove some theorems on centers of gravity. He was actually able to prove some extensions to Archimedes' theorems. You see the very irregular figures down there on the bottom of your screen. Those figures are very simple to find the center of gravity because of their symmetry. Of course, Archimedes took this much, much further with very irregular kinds of shapes. And apparently Galileo made a few contributions in that vein and impressed some of the mathematicians of the day that this young fellow did have talent. So he winds up having that 3-year stint in Pisa, not renewed. And again, through the help not only of Ricci, but also other members of the court, in Florence, he lands, of all things, the chair of the chair of mathematics is empty in Padua, over in the Republic of Venice, a very prestigious post. The University of Padua, then as now, is a very well thought of university in all of Europe, especially for math, science, engineering. And so he earns this post. And it's kind of tentative at first, but he works into it, and stays there for 18 years. So again, another contrast between Kepler and Galileo. Kepler taught for 6 years on a high school level, and after that became a member of the court. Galileo taught in the university for 21 years, but he was totally self-taught in his profession of mathematics and the various branches of mathematics, right? There was arithmetic, geometry, astronomy, and music. And he had very good backgrounds, in a lot of that stuff, luckily, that he could actually teach himself what he needed to know. And it is there at the 18 years of Padua, where he does his great research on the theory of motion, which we'll get to at the end. One of the great stories of Galileo happens during this time when he is at Pisa in that 3-year stint as a low-level lecturer. The story of refuting Galileo that things would drop according to their weight. Something that was much, much heavier would drop much, much faster. And he climbs to the Tower of Pisa and shows that, in fact, that's not the case. This is a story he tells at the very end of his life. And historians of science really don't know if it's true or not. There's nothing in anything about the records of Pisa that this actually happened. And many other people did this experiment to refute a lot of Aristotle's ideas about motion. And it is here, right, at Padua, that he gets that copy of the Mysterious Cosmos from Kepler, and writes that really kind of crazy letter of thanking him and thanking you being my friend, and I'll read it and with great interest and let you know what I find, and that's it. Nothing happens until we find him at the end of his career at Padua, that he writes. There's another exchange, correspondence between him and Kepler. And we come to that point here, at the end of his tenure at Padua, because he gets himself out by not inventing the telescope. That's now well known that he did not invent this telescope. He heard about these spy glasses that were being sold as novelties on the streets of Europe. He heard about it, and as the craftsman that he is, he was able to put together glass, grinding his own lenses if need be, to develop kind of by trial and error what we now call the Galilean telescope, of the objective lens being convex and the eyepiece being semi-concave. This is not as efficient a design in terms of magnetism, magnification, etc. The one advantage that it does have is that the image is upright, whereas in the regular refractor, the image is upside down. But this is the telescope that he used. He got up to a power of 30, we're told, and that picture there on the right is the Mona Lisa of the great museum, science museum in Florence. It is their pride and joy. It is the centerpiece of their collection. An example of one of the powerful telescopes made by Galileo. It's very exciting to go see that in Florence. And so it is here where he publishes, after studying just for 3 months, making observations. Here he publishes the Sidereus Nuncius, the Starry Messenger. Again, I think these discoveries are so well known, particularly to an audience like this, seeing more stars that you can see than with the naked eye, which tells Galileo, by the way, that these stars must be of different distances. And we don't really quite know, is there a firmament? Is there, in fact, a celestial sphere? Because once Copernicus no longer needed this sphere to be rotating, right? Since it is the Earth that is rotating each day, once the fixed spheres are no longer rotating, do we really need a fixed sphere at all? Maybe these stars are not all the same distance away. And one of the things that is suggested to Galileo by seeing different stars of different brightnesses, and ones that you can't even see with the naked eye, is that maybe, yes, maybe stars are at a different distance away. And maybe, who knows how far out stars will extend. And again, resolving the Milky Way. The surface of the moon was a great shock. That's the first thing he turns his attention to. I know this group will agree with me that the first time you ever get your hands on a telescope, no matter what age you are, the first thing you will look at, the most dramatic thing, the most fun thing, is to look at the moon. And that's exactly what Galileo did, and made those discoveries about the Earth-like nature of the moon. And he saved the best for last, the four largest moons of Jupiter: Io, and Ganymede, Europa, and Callisto. That's not the names that he gave, but I'll come to that in a minute. But here is, in the Starry Messenger, here is some of a page of how he is looking at Jupiter each night. You can see the dates. These are December 7th, 8th, 10th, 11th, 12th. He's mapping what he sees each night of these little stars that are going around the great star of Jupiter. And the first night he sees 3, well, 2 on one side, 1 on the other. And then he sees all 3 on one side. Then all of a sudden it's gone, and only 2, et cetera, et cetera. And what he realizes is that he is looking at moons going around Jupiter. This is probably cosmologically the most important discovery that he makes during the work of this of the Starry Messenger. And so here's just some pages from the Starry Messenger. Here's one of his maps of the moon. And here is his map of a constellation where the big stars are the stars that you can see with the naked eye. And he shows how many more stars you can see with the telescope. At one point he says that I can see 70 to 80 more stars in the constellation Orion with my telescope than you can with the naked eye. Remember, this is way before light pollution. This is when you're talking about very, very dark skies. And he can see more stars, of course, with his telescope. In terms of the names of the moons of Jupiter, he of course calls them the Medicean stars for the House of Medici, for Cosmos and his brothers, the Grand Duke of Florence. He wants out of Padua. He wants to go back home to become a court mathematician, and this is his ticket out by naming these stars after the great court Duke and his brothers, and gives his finest telescope, his most beautiful, most powerful telescope, as a gift to the Duke. But in fact, his names did not stick, and the names that did stick actually come from Kepler. He dips back into mythology and finds some figures that are related to Jupiter. And he says, I think, therefore, I shall not have done amiss if first is called by me Io, and the second Europa, and the third, on account of its majesty of light, Ganymede, and the fourth Callisto. And in fact, these names that Kepler gave did, in fact, wind up sticking. And here's just another picture from the Starry Messenger of that essay, of the picture essay of the changing satellites of Jupiter. The word satellite, by the way, a word coined by Kepler. And so Kepler, I showed, sent a letter of support to Galileo. Galileo thanks him very much. That incredible letter, that Caligula letter, as a colleague, saying if we could only could laugh together at the stupidity of these philosophers. And this is the second and last letter that Galileo ever writes to Kepler. So yes, he does win the title of philosopher and mathematician to the Grand Duke of Tuscany. Remember, Ricci was just the mathematician to the Grand Duke. It was very important to Galileo that he add to his title the philosopher, and he lobbied for that, and the Duke did allow that. He was also given the chair of mathematics back at Pisa, which I'm sure he felt very justified, smug about that. He never taught a day in Pisa, was just a court mathematician. Another interesting contrast, right, between Galileo and Kepler. Galileo was born to semi-nobility. Galileo was comfortable in the court. Galileo always moved in the circle of nobles, of the highest reaches of academia and of the court. Kepler, no, not at all. Yes, he found his way into work for Tycho, and was in fact given Tycho's new position, but not with anywhere near the prestige of a Tycho, not even close. He was still a nobody in 1600, and they had to find somebody to give the title, so Rudolf gave it to Kepler for some miracle, because he certainly was the most talented person on the staff. But just to show that his salary was 1/4 the salaries of Tycho's, show Kepler never moved in circles like this easily. When, for example, in 1611, when Rudolf had to abdicate, he was just getting sicker and sicker, and his brother took over. His brother threw him out of Prague. He had to go to Linz to live. And then he had trouble at Linz because he had some kind of a technical theological dispute with the Lutheran powers that be in Linz, and they virtually excommunicated him, if you can do that in the Lutheran faith. He was not allowed to go to any church, any services in Linz. He had to go to services, some miles away out of the town area. He was, made an anathema to the religious community because of his theological beliefs. Didn't help, of course, that at that point during this time, his mother was accused of witchcraft. Yes, his mother, which was a very serious charge in those days. Many women were burned as witches in Germany during those times. It was a charge to be taken very seriously. He dropped everything and went to the aid of his mother, hired lawyers, went there himself for the defense, ultimately did get her off. But that didn't help him with the religious community either, that his mother was an accused witch. So he was kind of an outcast, really, for the rest of his life. He had a very sad life, but yet he kept producing these incredible works of astronomy. Right, he kept producing the harmony of the worlds, and the epitome in 7 volumes, and the great tables, the Rudolphian tables. Where did this that's what he did. Without any help. He had no students, he had no assistants, he worked by himself. Another, by the way, interesting contrast between Kepler and Galileo. Galileo was a very good teacher, taught for a long time, 21 years. He had many famous students, people like Castelli, who wound up taking his old job as professor of mathematics at Pisa. There are people in the history calculus books like Torricelli and Cavalieri, who did great work in work on infinitesimals, the geometry of infinitesimals, which will ultimately lead to integration. These are great mathematicians and scientists of their own right, Torricelli, the inventor of the barometer. These were all at one time students of Galileo. Galileo was, when he wanted to be, a very, very personable man, a very good friend when he wanted to be, and obviously a very good teacher, very much of a nurturer of talent. And you can even see that in that first letter to Kepler. the young 25-year-old, giving him all that kind of support. He was able to do this kind of thing, but somehow or other, it did not stay with Kepler. He could not keep that up, did not try, had no energy for Kepler. So he does become the philosopher and mathematician to the Grand Duke. Two more great discoveries of Galileo while he is at the court is the phases of Venus. He first of all have to mention he begins to observe Saturn. He sees that there are ears on Saturn. You can see the picture. Here's the figure of Mars, the male figure. Here's the figure of Jupiter, and here's the figure of Saturn. And he sees these, whatever these are. He can't figure out what this is. Are they ears, or maybe there are two moons that are stationary moons on either side of Saturn? He can't figure out what this is with the telescope that he has. But much more importantly is the phases of Venus, which, by the way, is suggested to him by one of his students, Castelli. Castelli says, you know, if Copernicus is right, and now that you're telling us that you can see these planets as disks in your telescope, take a look at Venus. According to Copernicus, Venus should have phases just like our moon, whereas Ptolemy's system, since Venus is always in front of the sun, Venus is always between us and the sun, Venus will always be backlit and will not have full phases. And here is Galileo's famous pictures of his study of the moon as we go through the orbit cycle of the moon. Not only are we going through phases, the moon is getting more and more, less and less lit. You can see the Venus sign here, the female sign. But you can see that they're getting bigger and bigger in his telescope. Yes, and look, yes, as Venus gets closer to us, coming around in this inferior conjunction, yes, it will in fact get closer to us and therefore be bigger in his telescope. This is just a marvelous picture. And what this does, pretty much it puts the death knell onto the Ptolemaic system. Because Ptolemy, I mean, you know, the place where Venus and Mercury did bounce around for a while. Was it before the sun? Was it all after the sun, etc.? But Ptolemy finally came down with his authority and said, no, Venus and Mercury are both before the sun. They are lower, as they would have said it to the sun. And this was now inherent part of his model. And since the phases of Venus proved that this was not the case. And so at this point where the Ptolemaic model begins to disappear, and the rest of the astronomers, very much the group of Jesuits in the Roman college, very, very expert astronomers, they began to move to the Tycho system. The Tycho system keeps the Earth stationary, and everything else, of course, is going around the sun as the sun goes around the Earth. Kepler and Galileo had no respect for this model. They saw it for what it was. It's just simply moving the axis, the stationary axis from the sun to the Earth. The system is mathematically completely equivalent to Copernicus's model. So it was really just a device to keep the Earth stationary. The other final, the final discovery of Galileo really ends his creative time. Remember, he did all the motion stuff back at Padua, and this really is the last of his great discoveries. Remember, telescopes are being invented and built all over Europe. People are starting to look at the sky just like he is. And finally, the sunspots, not surprisingly, gets into a priority dispute with one of the Jesuit astronomers who claims that he saw them first, and there's a big dispute back and forth. But the difference here is, never mind who saw them first, the Jesuit astronomer who is making the claim about this, namely the Father Schreiner, is not saying that these are spots on the sun. These are kind of like clouds going across the sun, or maybe moons that are moving through the sun. And Galileo says, no, if you study the sun, the spots, every day, day after day, week after week, what you will see is that these spots are on the surface of the sun, and they're actually not moving on the surface of the sun. In fact, it is the sun that is rotating and moving the spots along with it. And this is just remarkable. If anything was supposed to be perfect, the perfect ether, it of course would be the sun. Not only is it not perfect, do they have these dark spots, but the sun is actually rotating just like the Earth is rotating. So this is a remarkable discovery of Galileo's. And you may find it remarkable that here in 1612 is the first time Galileo comes out in print supporting the Copernican model. Yes, he's 49 years old, and he finally has the nerve to say, I'm a Copernican. I believe that the Copernican system is the most real, the most beautiful, etc. So very, very, very interesting. And like I say, he gets into a very nasty match with Father Schreiner, who's a very powerful Jesuit, very learned, respected astronomer, part of the Roman College. And it's nasty on both sides, but Galileo can be very nasty. His wit is just cuts you right down. His sarcasm is famous for it. There are many quotes I could read to you that we have no time for, that he is just a master at the polemic. So yes, Galileo goes into many years of controversy. His research days are over, and he's basically fighting with mostly with the Jesuits. He's fighting with the astronomers. He's fighting with the philosophers, but he really gets into trouble when he starts fighting with the theologians. And that happens with the famous letter to the Grand Duchess Christina. Story is that she starts asking questions to Castelli, of all people, at one of her breakfast soirees about these discoveries of Galileo, and don't they kind of conflict with the scriptures? So Castelli writes to Galileo and says, she's a very powerful, influential woman, and she's asking some very hard questions. I think, you should address them. And he finally gets around to addressing these at the end of 1516. The letter is not published, but it is an open letter, very common in those days, distributed widely. And this is where he uses the famous phrase, not invented by him, but actually by the librarian of the Vatican, a bishop, says, the Bible, the intention of the Bible is not to teach how the heavens go. It's how to teach how to go to heaven. Did I say that right? How one goes, it's to teach how one goes to heaven, not how the heavens go. He goes much further in the letter. He starts telling these theologians how to interpret the Bible, that sometimes you have to interpret the Bible differently than you are, because when science comes up with some kind of a truth that can be shown, then that means that your interpretation of the Bible is wrong, and you're going to have to. This did not go down well. This did not. And he really makes just a whole battery of enemies, and historians of science do point to this letter and the brouhaha that it raised, particularly with the powerful theologians. And most of the people on the Inquisition, they were theologians. They weren't mathematicians. They weren't philosophers. They were these guys that he got mad at him. So the famous year in 1616, he is pulled in by the Curia. Again, we can't go through the details. I have a nice reference to a beautiful film about Galileo's life that you can see all of this in detail. But I think I really must move along. And he is ordered not to hold or defend the Copernican theory. You can hold it hypothetically. You can hold it as a calculation device. You can hold it to the degree that you are a mathematician. You cannot hold it as in your position as a philosopher. This is something, as the edict comes down, or the opinion of the Inquisition comes down, the sun is the center of the universe, is absurd in philosophy and formally heretical. And that the proposition that the earth has an annual motion is absurd in philosophy and at least erroneous in theology. So it's bad. They don't like it. They aren't buying this at all. This is the time when Copernicus's book on the revolutions of the heavenly spheres is in fact put on the index. Okay, it's put on the index until it's amended. Copernicus had been around for a long time. Astronomers had been using it. Even the church had been using it as a computational device. So they made changes, like a chapter heading would be on the demonstration that this motion is blah, blah, blah. They would change that to on the hypothesis that this motion is blah, blah, blah. And they made little changes like that. And once it was amended like that, then the faithful could read it again. They treated the work of Copernicus really with kid gloves. And Galileo was also treated with kid gloves. He was warned, everything will be fine. You're a very famous man with the Starry messenger, and everything is good. Just don't hold and defend this as the truth. You keep pushing the envelope, pushing the envelope. This is the time when he thinks he's developing a theory to prove that the Earth is moving. It's the tides. The motion of the tides proves that the Earth is moving, which is completely wrong. He just won't give up on this. And I'll mention a little bit later why historians of science say that, why he will not give up on pushing the absolute truth of the Copernican paradigm. Among all the controversy, we can't leave Galileo, and we can't leave his writings without that very, very famous quote of the mathematical universe from the Assayer. This comes from another controversy about comets with another Jesuit astronomer. He treats this poor guy, Father Grassi, even worse than Father Schneider. It really makes a ridicule of him. The irony is that Father Grassi is right, that comets are actually way up in the stars, moving through the orbs of the planets. And Galileo said, well, I don't know, maybe we need more data to look at this. It's possible that it's just some kind of a light kind of illusion or something that's making this happen. Just being just a general pain in the neck about this thing, more just to kind of get after this guy who apparently had no respect for us. If you read pieces of the Assayer, it's just brutal. But in all that is one of the most famous quotes in all of science. Philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It's written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one is wandering around in a dark labyrinth. This is one of the most famous quotes in all of science. If you've done any reading about the scientific revolution, if you've done any reading about general science, and the group I'm talking to, I know, has done this, we have all come across this paragraph more than once. If it's not the most famous, it's certainly in the top three. But Galileo begins to glide again. He's elected to a very prestigious academy in Florence, Scientific Academy. And most importantly, as far as he's concerned, one of his very good friends, Cardinal Barberini, is elected Pope. The old Pope dies, and he takes on the name of Urban VIII. And this is a friend and patron of Galileo. Galileo goes to Rome soon after he is elected, and he wants to press his case to the Pope that we have to change the church's teachings about this sun-earth thing. This is not important. This is not what the Bible should be about. What historians of science have pretty much have convinced each other of, that Galileo was a very good Catholic, and he wanted to protect the Catholic Church from this era, that the Catholic Church would look foolish about something that they didn't have to look foolish about. They didn't have to hold to this strict, whatever you would call it, interpretation of the Bible. One of the famous ones is the story of Joshua, where he prays to God to hold the sun still in the heavens, so he would have more time for the battle to defeat his enemies. Phrases like this prove in the scripture of the basic Ptolemaic system. And at one point, he makes a very powerful statement in one of his writings. He says to the church, he says, don't put the faithful in the position where things that they can see to be true from reason, you insist that if they hold them, it must be a sin. Don't put people in that position. It is a losing position for you. That if things that they know to be true, that they can see to be true, and you have it that if you believe these things, you're committing a sin. Don't do that. This was his great motivation, and he goes to the Pope. He again is a very good friend. He gets 6 private audiences with the Pope over a few weeks, and he's pressing his he's pressing his point about trying to move the church along, and the Pope is having none of it. And he says, Galileo, you've got to stick to the edict of 1616 of Cardinal Bellarmine. That slide kind of went by, so I don't think I mentioned his name, that you can't hold and defend. You can hold it as a mathematician, but you cannot hold and defend this as the truth. This is our position, and we're not going to move from that. So Galileo says, well, okay, I've been thinking of writing a book, and the book would be like a fair discussion, debate about the 2 great systems, the Ptolemaic system and the Copernican system. It'll be very, very fair, very objective, but I think will make a great contribution to the discussion to get all the good arguments out on the table. Pope says, okay, that's fine. You can write your book. Just make sure you don't hold and defend the position, the Copernican position, as the truth. And one more thing the Pope says, which will become very important for us. At the very end, when he's pushing about the tides, the Pope says, Galileo, your theory about maybe the tides show that the Earth is moving, God in his infinite power, he could make the tides move for all kinds of reasons, for your reason, for other reasons, for reasons that we could never know. And so there's no point in you pursuing this, because we will never know why the tides, why the oceans move the way they do, because God has so many options to make that happen. So hold that thought until we get to the dialogue and to his condemnation. And so we have the dialogue.
Peter, can I
Yes,
interrupt you? We have a couple of questions piling up.
please. Okay.
So, all right, so this one's a bit of a throwback. It's been pending for a little bit. Rick asked, to go back to Kepler, did Kepler use whatever formula astrologers espoused, or did he make things up? I asked because it was said that he had a reputation for accurate predictions. Do we have a record of whether the math he used? Do we have a record of the math he used for any predictions?
That's a very good question. When he cast his horoscopes, did he use his new theory or did he use his old theory? That is a very good question. I've never seen that question raised or discussed in all my readings. My guess would be that, these tables from which the astronomers would make and the astrologers would make the predictions of what the configuration in the sky would look like. There were many different kinds of tables that could be used. Now, his Rudolphian tables didn't come out until 2 years before he died. So I think it's a good guess that he wasn't using his most modern tables based upon his theories to make all those horoscopes that he made, during his early part of his career. So he was using some other tables. Being a very avowed Copernican, I wouldn't be surprised if he used the Copernican tables that were produced soon after Copernicus died. Man by the name of Erasmus Reinhold, I think, produced, actually, he was not a holder of the Copernican theory, but he saw the value of it as a computing device and created a set of tables based upon the Copernican motions to be able to make predictions. And that may have very well been the tables that Kepler made to cast his horoscopes.
Yeah, so Rick's follow-up question was, he was wondering if Kepler cheated on the math to justify giving answers that he thought were wise. Is
That I don't know. I know he had a reputation. He made one prediction to one of the kings that just by sheer luck turned out to be right. A really big deal in his horoscope. And from that, it's like, one will make your reputation. It's very hard to tear it down. He then, going forward, had a very famous, he was a great prognosticator using his horoscopes. Exactly how what technical devices he used to cast his horoscopes, I have never read about that part of Kepler's work.
okay. And from Claudio, we have 2 questions. The first is it known whether Galileo drew phases of Venus from a single sequence of observations, or are those drawings a summation of multiple observations?
No, apparently because they were done in such a short period of time, this work comes out on the phases that they were done through one observation, coming around from one conjunction to the other.
And then the second question is, why didn't Galileo go blind earlier in his life looking at the sun as much as he seems to have done?
That's a good question, and most historians are convinced that Galileo was smart enough to be able to project the sun onto a screen from a lens, and he did not have to stare at the sun.
Okay. All right. That's the backlog.
Okay, so I'll continue. Eric, should I continue?
Oh, yeah, sure.
Okay. All right. So we come to the dialogue, written, published in 1632. This is written in Italian. It's written for the educated layman. And you can see a couple of pictures from here are the three characters of the dialogue. There's someone who represents Galileo, someone who represents the Aristotelian philosopher, who he names Simplicico. And there's a Segredo, who is kind of the, fair, educated layman who will, listen open-mindedly to all the arguments. And you can see here's the Copernican system, and he's not going to leave out his great discovery of the 4 moons of Jupiter. And we all recognize this picture of the Copernican explanation for retrograde motion. And basically, his argument is in 3 parts. First of all, it's interesting that he completely ignores Tycho's system. He also completely ignores all of the work that Kepler has done in this work. Kepler is now dead. All of his work is in. All of his work is published. He completely ignores Kepler's work in the dialogue. He ignores Tycho's system for the reason that I gave. He had no respect for Tycho's system. Tycho's system was clearly just a just a propped up version of the Copernican system. Also, he was trying, his main scientific objective in the dialogue was to show that all these arguments about how the Earth can't be moving, all these arguments coming from the theory of motion of Aristotle, that if the Earth were moving, all these terrible things would happen. Clouds would go by and birds couldn't land on branches, and if you dropped a ball from a tower and the tower was moving through space because the Earth was turning, the ball would land away from the tower far away. And many of these classic arguments, he wanted to show that all those arguments were invalid. Okay, that the Earth, that the motion we see on Earth would be exactly the same whether the Earth was moving according to Copernicus, spinning on its axis and going around the sun, or stationary. That was his main scientific aim, and he very successfully succeeded. Yeah. His second part, he went through all the discoveries of the telescope, bringing everybody up to date, all the things which support the Copernican hypothesis, and finally, he can't resist his third chapter is on his proof of the tides. This is of course completely wrong. So let me go through what I feel. Oh, okay. If I can read this, let me see. The words are okay. He went away. He was very disappointed in Kepler with his theory of the tides. Kepler said, no, the tides are caused by the action of the moon, and even to a slighter degree, maybe the sun, but it is the moon that is causing the motion of the ocean with these tides. And Galileo was very, very disappointed in Kepler. He says, among all the famous men who have philosophized about the tides, I wonder more at Kepler than any of the rest. For he is, and this is funny, guys, but I can't read my own thing because the Zoom words are in the way. So let me just paraphrase. Probably you can see it. Oh, I can see it on my other screen. Among all the famous men who have philosophized about the tides, I wonder more about Kepler than any of the rest. Though he is a free and acute genius, he has lent his assent to the moon's dominance over the oceans and to other occult happenings and other such childishness. This is how Galileo felt about how could the moon so far away have anything to do with the waters here on Earth. It's just a silly, childish, occult idea, the idea of occult being totally hidden, nothing that we can see for a cause, and very disappointed in Kepler holding that view. But here is a classic picture explaining where Galileo was trying to show that the motion of the Earth will not affect how we see things moving. They'll move just as if the Earth was stationary. And an example that was always used was dropping a ball from the mast of a moving ship. If, according to Aristotle, if you dropped a ball from the mast of the moving ship, as the ship moved on in the water and the ball was moving straight down, according to Aristotle, to the center of the Earth, it would move, and therefore the ship would move out from under the moving ball and would splash, away from the mast. Galileo said, no, that's not what will happen at all. The ball up on the mast already has the motion of the ship. And when you drop it, yes, it will drop in free fall. It will fall as if it were being dropped, but it'll also keep that motion. It'll keep that forward motion because there's nothing to slow it down. There's nothing to speed it up. This, of course, is the law of inertia. He says, in fact, if you were to look at the motion of the ball from the shore, what you would see would be an arc in which the ball is both moving forward and moving down. Okay? And he goes on, there's a beautiful piece in the dialogue where he describes how if you were down the bottom of a ship and you did all these kinds of experiments of dropping, water from a jug and seeing little gnats fly around if the ship was at anchor, and then you sent the ship out, as long as it was moving at a constant speed in a straight line, you were in this inside cabin, the drips of water would still drip down, straight down into the jug, just as before. The gnats would still fly around in all different crazy directions. Everything would be as it was. It's a very beautiful paragraph in the dialogue describing what we now call Galileo's law of relative inertia. And here's just another view of the law of inertia that he comes with experiment. He shows that when you roll balls on inclined planes, it'll go up to the height that it started with, as best you can show, making the resistance, making the friction as little as possible by abstracting the problem and doing the best you can with hard balls and very hard surfaces. He says, so what would happen if you were to roll the ball down one side, but you kept lowering and lowering the other side? Now, if it's going to, since the only resistance it's meeting, right, is gravity, if it's not going to stop until it reaches its original height, as you lower this thing down, it'll move further and further and further out until it finally gets to that original height. Well, what happens if you put the other side down flat? And it'll never reach that original height. What will the ball do? When will it stop? Never. There's nothing to slow it down. Without any friction, without any resistance, and without any gravity pulling it down, because it's not climbing up anywhere, it will move forever. And this is what Newton takes on as his first law of motion. A body at rest will remain at rest, and a body moving at a constant speed in a straight line will continue to do so unless it is acted upon by an unbalanced force. And so to finish up the story, Galileo is put under house arrest. He is shown to be guilty of violating the edict. He did hold and defend that this work was not objective at all. Everyone could see through that. And the decision was that this was, shown to be formally heretical and all that bad stuff. And his book was put on the index and the dialogue and not taken off until 1822. For good measure, all of his publications were forbidden. Anything he did write, anything he wasn't supposed to publish anything anymore. He wasn't supposed to republish anything of his old works. They really came down on the hammer on this, and for good measure, they also threw all of Kepler's works on the index as well. The Pope was very, very angry and very, very vindictive about the dialogue for this reason. The last page of the dialogue, when he finishes his theory of the tides, he has Simplicico. This is the last thing that Simplicico says. He says, I don't know about your arguments about the tides. Are kind of complicated for me. I'm not convinced. But I tell you one thing that I do know. A very, very smart man once said to me that God in his powers could make the tides appear and move and behave the way they are in many, many ways. Your way is a possibility, and many other ways that we would never know. And so how would we ever determine what was the cause of these tides? This is exactly the argument that Urban made to him in 1624, and he puts it in the mouth of the simpleton. Well, Galileo's enemies jump on Galileo, tell the Pope he is insulting you. This is the ultimate insult, putting this in the mouth of the simpleton. Your advice, your caution to him to try to go slow and not push this too far, this is how he repays you. And yeah, he got the full brunt of the power of the Pope. His last works, the last great work, of course, is the Discourse on Two New Sciences, which I'll say a few words in a moment. But it is interesting as you look at these other bullets in the slide. All of a sudden, we find out he's now under house arrest. He can't publish anything. He can't write anything new. It's very funny story. At the trial, when he admits, he said, well, maybe I was a little bit favoring the Copernican system a bit too much. Maybe I wasn't exactly as fair as I could have been. I'll fix this in my next book. Pope says, there's not going to be a next book. You're not writing anything. What next book? This is just classic Galileo. He's going to fix it in the next book. But what's interesting, what comes out when he winds up back in Florence, back in Chetri in his home in the house arrest, all these publications start coming out of the North countries, out of France, out of England, out of the Netherlands. All these, finally, the letter to the Grand Duchess is finally published, officially published, both in Italian and Latin, and there are other things coming out. Translations of the dialogue in Latin was written in Italian. The States General awarded him 500 florins for his idea of solving the longitude problem. And we know the longitude problem of having a clock that everyone can see anywhere in the world, and then knowing what the time your time is and what Greenwich time is, you can figure out your longitude. Galileo had the idea of using the moons of Jupiter as a clock that everyone can see. Theoretically, a very good idea. It just wouldn't work with the technology of the day. And finally, a year before he dies at 77, he's blind in both eyes. He begins working on an application of the pendulum to develop a clock construction. His last student there is Viviani, who describes all of this work that Galileo did in these last years, and dies finally at 78. So let us look very quickly at just his work in the two sciences. He first of all wants to study free fall. He has the genius to know that if he works on an inclined plane, he will be looking at the same basic phenomenon. The same mathematical laws will apply. It'll just all be diluted to something that's slower that we can measure, because given the clocks of his day, dropping something in free fall all happens too fast. So he starts with the hypothesis that the velocity will increase regularly, one tick at a time. Whatever the first speed was, after the first second, it'll be twice that speed in the second second. It'll be 3 times that speed in the third second, etc. From that, he takes some data. This he can't take. He can't take this. He can't measure speeds, but he can measure the change in distance, and he can measure, therefore, the total distance. And he gets a law which looks like the distance changes with the time squared. And he does this experimentally, right, on the inclined plane. Then mathematically, he proves by mathematical theorems that if this hypothesis is true, if the speed increases like this, then the distance would increase like this, also to time squared. So his mathematical analysis agrees with his experimental results, and he takes that as tremendous support for the hypothesis that speed increases linearly with time. And this methodology is now used right throughout science today. Some hypotheses can't be proven directly, but you can build more and more and more support for that hypothesis by showing other predictions, in fact, will be so to support that hypothesis. And he goes further to analyze motion even beyond just free fall, finally coming with the analysis of a projectile, showing that it is a parabolic motion. He shows this first time in history. He takes 2 laws of motion, which he's discovered. He takes the law of inertia, where the forward motion will continue constant speed, and he takes that law of free fall of t squared, and he combines them mathematically and shows mathematically that trajectory will be a parabola. The first time in history anyone takes laws of nature and from those laws computes, calculates, predicts the trajectory of a natural motion. Don't think of Ptolemy and Copernicus and Kepler. They didn't do that. Okay? They had these preconceived ideas of what things had to be, right? Constant motion, constant uniform motion. Kepler had this 20 years of data that he found his laws empirically. He found them in the data. He had no derivation. This is the first time that anyone can show by mathematical analysis from more fundamental laws a result about the natural motion of something in nature. Okay, so that is the end of the second part. Eric, I'll hand it off to you.
So we have one question from Matori. Did Galileo ever make a systematic effort to observe stellar parallax in confirmation of the heliocentric theory? If
Very,
so, how did he explain his failure to find it?
very, very good question. I actually did a little bit of research on this question. I'm so glad you asked it. Um, Way back in the Sirius Cosmos days, Kepler asked Galileo this question, being the professor in Padua. Kepler has no equipment. He says, with your equipment, are you looking for the parallax of the stars, the way our master Copernicus predicted that would be, that we can't see because the stars are so far away? Galileo, of course, doesn't answer that question. But he does, in the dialogue, he talks about searching for the parallax. He even has an idea of how to do it. He wants to look at a star not on the zodiac. He wants to look at the star at the top of the, at the zenith of the celestial sphere. I'm sorry, not the celestial sphere, but the zodiac sphere, so that he'll get the greatest change, going from one side of the Earth's orbit to the other. He has a good idea how to do it, but he has nowhere near the technology to do it. Right? We know that this parallax is not found until 1828. 1828 is finally when that parallax is. But he did have, theoretically, a good idea of how to go about it, and he did try.
Okay. Does anybody else have any other questions, comments, observations? Okay. I just do want to make a time check. We're coming up for a 8:45.
I apologize for being so windy, but I only have a few slides left. This is the wrap up. Could you bear with me, guys? All right. So in summary, we have Kepler, the founder of celestial mechanics, right? His 3 laws of motion, his idea of looking for forces to explain why these motions are the way they are. Kepler saw no connection between this problem and, by the way, the work of Galileo, who worked with terrestrial motion of gravity here on Earth. His problem didn't seem to be related at all to Galileo's work. Here we have Galileo, on the other hand, the founder of the new science of motion that we just looked at. And Galileo saw no need for any forces involved with the planets. He had this notion not only of inertia, the correct idea, he also had this notion of circular inertia, almost going back to Aristotle, with this kind of natural motion of moving in a circle. If you're out in the celestial world, that once something starts moving in a circle, it can continue to move in a circle. This is not now spinning with rotational inertia. This is truly moving in a circle. Galileo has this misguided idea that things could continue to move in a circle, and this will explain why the Earth can be moving, and it will still, things on the Earth will keep moving on the Earth, will keep up with us, because it has this circular inertia as the Earth goes around the sun. So there's no connection between these 2 great pieces of work. They ignore each other's work. There's Kepler looking for the forces, and Galileo says that we don't need to look for them. It's just circular inertia. And so we finally come to Newton. We come to the connection. And here, as you know, the famous story, when Cambridge was closed down because of the plague, he was sent home to the farm. And I asked this question to my core class: how are you guys doing in terms of your productivity these months being cooped up? Let's take a look at what Newton did when he was cooped up at the farm. He mastered the mathematics of his day. He extended that mathematics, proved the binomial theorem, and beginning working on the calculus. He formulated the laws of motion. He developed the law of gravitation, and he investigated the constituent pieces of light, the breaking up of light into its spectrum. He writes, in the same year, 22 years old, that's what he is, I began to think of gravity extending to the orb of the moon, and from Kepler's rule of the periodic times of the planets, I deduced that the forces which keep the planets in their orbs must be reciprocal to the squares of their distance from the centers on which they revolve. I therefore compared this force, requisite to keep the moon in her orb, to the force of gravity at the surface of the Earth. A connection between the work of Galileo and Kepler, and found them to answer pretty nearly. This was in the plague year, the two plague years of 1665 and 1666. For in those days I was in the prime of my age of invention and minded mathematics and natural philosophy more than any time since. And so, yes, he derives the second law of motion, the famous F is equal to ma, and the connection is there between the force and acceleration. That's the missing connection that Kepler did not have and Galileo didn't even really look for. Just the idea of the second law of motion, continuing force will make something accelerate either faster and faster or moving in a circle, changing its direction, also represents an acceleration. And finally, I will not burden you with this. This is a little proof that you can derive Kepler's third law from his law of gravity. Okay, this is called the Kepler problem. This is what Kepler wanted. He wanted some fundamental law underneath all of his stuff that you could deduce his three laws, just as Galileo deduced the trajectory, the parabolic trajectory of the projectile. And this is what, among other things, Newton did in the Principia. And to sum up, last slide. When you look at Kepler's work and his attitude towards science, he was really from the classical school. He was looking for the mathematical plan that God had to construct the universe. And if you could find that, in a sense, you were done, because that was the plan. That's what God had done to construct the universe. And once we understood that, we would pretty much understand what we were looking for in that realm of knowledge. As he says in the quote that I gave, geometry is co-eternal with the mind of God before the creation of things. It is God himself has supplied God with the models for the creation of the world and has been directly transferred to man along with the image of God. Galileo is a much more of a modern scientist. Galileo sees the pursuit of science as open-ended, that you're always progressing. There's always new areas to investigate, that when we discover one thing, it'll open up questions to something else, much more of a modern idea. He puts it very, very beautifully in the third day of the New Sciences, after he says all the things that he's going to prove coming, that you're going to read about, all these things that I've just proven. He says, and what I consider more important, there have been opened up to this vista and more excellent science, of which my work is merely the beginning, ways and means by which other minds more acute than mine will explore its remote corners. And so we have these two men, very different approach towards science, but the famous quote of Newton, if I've seen further, it is because I have stood on the shoulders of giants, and we all know who he was referring to. Okay, Eric, I'm finished.
Sure. So we have another question from Matori saying, Mr. Mulhall mentioned you mentioned a good movie about Galileo. Can you give us the title?
It's right there at the very bottom. Galileo, Battle of the Heavens. You see it on the screen?
I will. Yep, I can see it, so I assume everybody else can.
Okay. The book that was based on is Galileo's daughter, a very beautiful, very unique kind of biography of Galileo. And this is a wonderful film. I really highly recommend it. Goes through all the stuff that we didn't have time to talk about.
So if anybody else has any questions or comments, feel free to hit the raise hand button by clicking on participants down at the bottom or typing something in chat, and I will read it for everybody. And before people leave, if you are willing, normally at the beginning of our meetings, we hand out a clipboard for folks to provide any information they're willing to share. Just helps us kind of know, well, who's coming to our meetings, where are you coming from, how did you find out about us? If you don't mind putting that into the chat, this way we'll have a log of that after the meeting. Don't feel that you are being forced, but that's something that helps us out. John is asking if there will be slides available for this. Now, Peter, I believe, is recording this. Will that be available online somewhere for?
Yes, I'm gonna, if I can manage this, if I can get my hands on the recording, because I'm a little new to the recording, where you being the host, Eric, my plan is to put it out on YouTube, and I will send you the link, and anybody who wants it from you or from me, you can reach me pretty easily. It's peter.mulhall@keene.edu. just my name, peter.mulhall@keene.edu.
That's spelled that right.
And I'll be happy to send that link to you.
Okay. I just typed your email address in chat. Hopefully I spelled it
Oh, great. Thanks, Eric. I apologize for being so long-winded, but as you can see, there was a lot to talk about. You can imagine how much I had to pare down.
All right. Last call for questions, and feel free to unmute yourself and speak as well. It doesn't have to be through chat.
Okay, I guess, Eric, we're done. I want to thank you very much for handling the questions and being a wonderful host for my talk. I appreciate what you did.
Oh, sure thing. My pleasure.
So
All right. I will not close the meeting, but I will
I will stop
allow
the recording on my side.